Hello, this is a key to the Unit 1 review. I'll be going through the solutions here, and I'll be kind of guiding you on some things that you should probably look at in your notes as we go along the way. Some of it I have pre-filled in here, and other things I'll write in as we go along. The idea was just to save some time with that. So to start off with here, this says review the names of the 23 pieces of lab equipment. So you have to know 23 of these different pieces of lab equipment. I have 4 of them here. I'll put the flashcards back online so you'll be able to access those and review those and just make sure that you know the different pieces of lab equipment here. So first one here, this is, you can see it has the pointy little finger sort of things there. So that's the Crucible Tongs. The other kinds of tongs are really round for grabbing beakers, and those are called beaker tongs. So these ones are Crucible Tongs. The second thing here is an evaporating dish. It looks like sort of like a bowl. It's like a ceramic bowl, and you put things in it to try and evaporate liquid to get it a solid that's dissolved in the liquid to come out. This last thing here, this is a crucible. All right, and then this one here is a utility clamp. So just make sure that you know those different things, and there are 23 different pieces of lab equipment you can gauge based on how you did here, how you do on the actual exam, but just make sure you're really clear on those things. All right, so for these lab safety questions, I kind of just have the rules written in here so you can kind of get an idea of that, and if you have any questions over those, you can ask me in person. Just make sure you're pretty familiar with the safety procedures we have. There are 2 safety videos online that I posted, so watch those if you need. Otherwise, this is just kind of an FYI, read these different things. Pause the video if you want to take a second to read them, or there will be a PDF version of this key online, which you can access as well. Alrighty, so down here for accuracy and precision. Accuracy, when we're talking about accuracy, we're saying like how close to the true value it is, or how right on it is. And so the idea here is that there's a true scientific value for anything, and if you're measuring it and you get that true value, then you have an accurate measurement. Precision now is a little bit different. It has to do with how small you can measure. And so when we say something's really precise, we mean that it can measure to a really, really small degree. And so think a ruler with a lot of marks on it, or if you had, say, something that like a microscope where you could measure something down to the micrometer, something very, very small, it would be precise. Another way that we use this is we say that we get consistent measurements over time. And it should make sense to you that these are a little bit related. If something has a lot of marks on it, then you should consistently get the same measurements on that device. Versus if something didn't have a lot of marks on it, when you estimate it, you might get some different values depending on the person using it, or depending on what you're feeling each day. You might get some different answers there. So that's precision. How small the measuring is, or how consistent you are with that. And then I use an example here at the bottom. I say, imagine that you had a digital clock and it's ticking up every 100th of a second. All right, so some of you might have seen this like on a stopwatch or something like that. So you see the 100th of a second scrolling by all the time, really, really quickly. And so that would be very, very precise to have a clock go out to the 100th of a second. Most clocks only go out to the second. Some only go out to minutes, but this one goes out to the 100th of a second. So it's very, very precise. But I said, imagine that it's an hour slow. If it was an hour slow, then it's not accurate because it doesn't display the correct time. Even though it shows the time out to a very, very precise level, it doesn't show the correct time, so it's not accurate. All right, so this next section here is on measurement. What we're going to do here is look and talk about what would be some reasonable sorts of things for the measurement here. So this first one is marked every 10, all right, and so you can estimate one past the decimal place that's marked. If this is marked every 10, and we've got 40 here, and we've got 50 here, this here is kind of in the middle. It looks like it's a little bit closer to 50. All right, so I'm going to call that something like 46. millimeters because that ruler is in millimeters. All right, jumping down to these graduated cylinders here. This graduated cylinder, it says 75 at the bottom, and then 5 marks up as 80, and then 5 marks up as 85. So each of these lines is 1. If each line represents 1, then we can estimate to the 10th place. We look at the bottom of the meniscus here. That looks like it's right on 81. All right, so we write 81. But I said we can estimate out to the 10th place. So if it's right on 81 and we're estimating out to the 10th place, it's 81.0. This next one is a little bit more confusing. If you notice here, this is 45 and this is 50, and there are 10 lines between them, which means each line is 0.5. So just to kind of get a general idea, like this line is 46, this line is 47, this line is 48. Okay, so we have this marked somewhere between 47 and 48. Okay, and really this line is 47.5 right here, right? So it's somewhere between 47.5 and 48. It looks like it's closer to 48. All right, and so I would say it's something like 47.8 here. So that is that. Be careful there because, you know, some people might be tempted to go even one step further. I don't think that our eyes can break things down to that extent. If you said like something like 47.82 or something like that, that means that you'd be breaking this down instead of into sort of 5 pieces like I was breaking it down into. It's like you'd be breaking it down into 50 pieces, and I don't think that your eyes are capable of doing that. And so what we're going to do is we're just going to leave it here. 47.8 seems like a reasonable estimate there. This next one, kind of along the same lines. So we've got 2, and then we've got 3 up here. So this is 2.2, 2.4, 2.6, 2.8. So it's somewhere between 2.6 and 2.8. It looks like it's, you know, kind of right in the middle, a little bit lower, but it looks pretty close to the middle. So I'm going to call it 2.7 milliliters. You might be able to, on this one, estimate it, because if you broke this down, if you broke down between those dots, something like into 20 places, you'd be able to get a little bit, you know, you might be able to estimate it there because this is only 0.2 between each dot, all right, and 0.2 is, you know, almost 0.1, you know, it's pretty small, and so you might say, all right, I can break this down into 20 little areas here and estimate it as something like 2.73. I think breaking something into 20 pieces is still kind of unreasonable, so I'm going to leave it at 2.7, but that's how that goes. So generally speaking, I'd say as a rule of thumb, if something isn't marked on increments that are like a normal decimal place, like if something isn't marked to the ones or to the tens or to the hundreds, still consider it, you know, whatever the level is kind of above that. So this one here is marked to the 10th place, but it's not marked every 10th place. And so I would say if it's not marked every 10th place, it's only as good as being marked to the ones place. And again, that might seem arbitrary to you, but if you want to talk a little bit further about how that works, we can talk about it. I won't put ones on the exam that are quite so confusing as these are here. All right, going on to the next one. We have thermometers here. This is kind of similar. This one is marked every, so we've got 37 here and 38, and so every mark is 0.2. So 37.2, 37.4, 37.6, 37.8, and it looks like it's, you know, a little bit more than 37.8. You know, I would call it something like 37.9. It seems like it's closest to. And the deal, again, there is you might be able to cut this space here but between these two lines into 20 sort of slots with your eyes, but I think that that's a little bit unreasonable, and so I would just leave it at 37.9. All right, and the units here are degrees Celsius. This next one, each line represents a tenth. All right, so this is 0, this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. And it looks like it is right on there. Oh, sorry. Each one of these is 1 degree. I was incorrect about that. So each one of these is 1 degree. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8. And it looks like it's right on 8. Now, if it's marked every 1, we can estimate to the 10th place. But we said it looks like it's right on 8 here. So if it's right on 8 and we estimate it to the 10th place, I'm going to call it 8.0 degrees Celsius because we can estimate it to the 10th place, but it was exactly on a number. So we still put the 10th place there. The 0 is a placeholder, but, you know, it's 8.0, okay? Going on, this section is on scientific notation. For scientific notation, you just have to think about how many places you'd move over the decimal point, and also whether it's a big number or a small number to see if it gives a negative exponent or a positive exponent. If we bump this over here, 1, 2, 3, 4, 5, 6 places, we get the decimal in the right place, just 1 non-zero to the left of the decimal point, so that becomes 4.5 times 10 to that. And since this is we moved it over 6 places, and this is a really small decimal, we're going to call this negative 6, because negative exponent on that 10 means small number. All right, continuing on. This one here is a very large number. All right, the decimal point is here after the last one. If there's no decimal point marked, we jump it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spots. All right, so it ends up being 3.4 times 10 to that, and because this is a really big number, it's a positive exponent, so 10 to the 12th. 25. This one, we'd consider it a big number as in being like larger than 1, okay, but it's not that big of a number. To get it in the right notation, we just bounce this over like 1 spot, boom. All right, and so it's 2.5 is what we get, and then times 10 to the first power because we just moved it over 1 spot. Okay, these next ones are going the other way. 7.67 times 10 to the 5th. Because this has an exponent of 5 on that 10, we know it's a large number. So we're going to be bouncing the decimal place over 5 spots here. 1, 2, 3, 4, 5. All right, which means we have to add some zeros there. All right, so we get 767,000. For the next one, 6.25 times 10 to the negative 4th. We're going to be bouncing this over the other way because it's a small number, so we're going to move the decimal place 1, 2, 3, 4 spots over here, fill it in with zeros, 1, 2, 3. All right, and so we end up with, and then I add another 0 up front just because it's proper notation. So 0 point and then 3 zeros, 1, 2, 3, 6, 2, 5. All right, for problem 6, it says 2.1 times 10 to the 0. This times 10 to the 0 thing is kind of funny. What that means, 10 to the 0 power, anything to the 0 power is 1. So 2.1 times 10 to the 0, that's saying don't move the decimal place over anywhere. And so that just becomes 2.1. All right, a weird case there, but 2.1 times 10 to the 0 is just 2.1. Alrighty, next thing here, this is actually just putting things into your calculator, so you should practice the skill of putting things into your calculator. The way I do this is I say like 3.5 E5 plus 2.01 E4. Alright, put that into your calculator, and you should get 370,100. All right, this next one, 2e negative 5 divided by 5e negative 6. Put that into your calculator. You should get 4 from that. The next one, 7.8. This one is a little bit confusing because there's multiple, there's a set of parentheses here. So it's 7.8 E4 plus 5.6 E5. And then we're going to take the answer to that and we're going to divide it by 8.5 E3. the fourth, and put that in your calculator. You should hopefully get 7.51. All right. So that is how that works. If you have any questions about the calculator or how to use the calculator, let me know. Make sure that on test day you show up with a calculator that you know how to use. This next section is just counting significant figures, so I'll go through that really quick. 2509, that's a sandwich zero in that one, so that one counts. So there's 4 here. 0.002050, these 2 zeros are leading zeros, those don't count. The sandwich zero does count. The trailing zero, if there's a decimal point, counts as well. So this is 4 significant figures on that one. 9800 point, that point says the trailing zeros matter, so this one has 4 zeros. And then this last one, that over bar says that those 2 zeros matter and that the other one doesn't. So 245,000, the 2, the 4, the 5, and the 2 zeros both count, so there's 5 here, and then that last zero is an insignificant zero. Going through in this next one, some math with sig figs here. The first one, 22.89 minus 0.02. We're using the addition subtraction rule on this one. This goes out to the hundredths place. This one goes out to the hundredths place. We look at the place value, the least precise decimal place. Since they both go out to the hundredths place, our answer should go out to the hundredths place as well. So 22.87 is what we end up with there. 3.55 divided by 5. This is the multiplication division rule. We're counting sig figs for multiplication and division. That's 3 sig figs. This is 1. Our answer should have 1 because that's the lower number. 3.55 divided by 5 gives us 0.7. And I think you would get something slightly different, but you need to round it to that. All right, 2800 minus 850. This one's a little bit weird. So if we have a number written out like this, those zeros at the end of 2800 are not significant zeros, meaning they're not known values, which means the last known digit on this 2800 is the 8. For the 850, the last known digit there is that 5. So the first number we know out to the hundreds place, and the second number we know out to the tens place. So our answer needs to be rounded to the nearest hundred. If you put it in your calculator, you get 1950. All right, but we need to round this to the nearest hundred. So we say, all right, that would be 2000. There's a problem here now, though, because if you write 2000, it looks like you only are confident to the thousands place, because it looks like all 3 of those zeros are insignificant zeros, so you only know it out to the thousands place. So what we need to do is we need to include an overbar over this 0 at the hundreds place to say, we know it to the hundreds place. We don't know tens, we don't know ones, but we know that 0 in the hundreds place is correct. All right, so, yep, that one's a little bit confusing. Ask me if you have any questions about that. Moving on down here to the conversion problems. These are all pretty straightforward, but, make sure that you're practicing this and that you're good at doing it. The first one here says convert 580,000 centimeters to miles. So we have to think, okay, we're going to start with 580,000 centimeters. Oops, that says 58,000. 580,000 centimeters. Next, we have to think of the path. If we're going to miles, we can go from centimeters to inches, inches to feet, feet to miles. All right, so that will be the path. So we go centimeters here, cancel out, to inches. We know that there are 2.54 centimeters in 1 inch. All right. We know that there are 12 inches in 1 mile. Oh, sorry, 12 inches in 1 foot. Jeez. 12 inches in 1 foot. We know that there are 5,280 feet in 1 mile. All right, so if you take those and multiply them and then divide what you get in the top by what you get in the bottom, you should end up with 3.6 miles here. All right, this next one, 3,000 milliliters to deciliters. Now, a lot of people got confused about this one in class because it's mixed in with these other ones that are not metric conversion. But if it says milliliter to deciliter, those are both metric things. And so the way that you convert this is by using that acrostic that King Henry died by drinking chocolate milk. All right, and so we're going to go from milliliters to deciliters. Milli, 1, 2 spots over to deci. All right, and so we take that 3,000 and we jump it over 2 spots, 1, 2 spots. All right, and that's 30. All right, so it ends up being 30 deciliters. All right, continuing on here. 3,000 milliliters this time to quarts. All right, milliliters to quarts is not a metric conversion, so we got to go through the conversion table. 3,000 milliliters is our starting point. Up on the top, there's a conversion factor going from milliliters to cups. So there's 237 milliliters is 1 cup. And then you also know that there are 2 cups in 1 pint. And there are 2 pints in 1 quart. Okay, and so if you go through and multiply across the top and multiply across the bottom, take the top divided by the bottom there, you end up getting 3.16 quarts. All right, next one, converting 25 cubs to nubs. This one here is with those nonsense units, but there's the key up above where it tells you the different conversion factors in it. We're going to start with what we're given here, so we start with 25 cubs. If you look and try and make a path, you can see that we can go from cubs to chubs and then from chubs to nubs. All right, so the first one, cubs to chubs. We know that there is 1 cub for every 16 chubs. All right, additionally, we know that for every 2 chubs, there are 7 nubs. If you go through and do the calculations there, you should get 1,400 as your answer, and the units on that are nubs. Okay, then we have this challenge question down here. In order to think about it, it says how many meters are there in 1 kilometer? Well, if you remember, kilo means 1,000, or if you want to just do the metric conversion, you should get that there are 1,000 meters in 1 kilometer. All right, so we'll use that as one of our conversion factors. We start off here, 120 kilometers per hour. When we say kilometers per hour, we put the kilometers in the top and the hours in the bottom. All right, and then from that conversion factor that I just gave you, you know that 1 kilometer equals 1,000 meters. And then from the conversion table up in the conversion factor up in the table up above, you can see that the 1 meter is 3.28 feet. And then we're in feet, okay? So we wanted to get from kilometers to feet. We've done that. Kilometers cancels out, meters cancels out. We're in feet. All right, now we need to get rid of hours and get the hours into seconds. So hours is on the bottom, in the left bottom corner. So we're going to make hours up here to get it to cancel. So we can't go from hours to seconds directly. Some of you might know that conversion factor, but some of you don't. So we'll go from hours to minutes. In 1 hour, there are 60 minutes. All right, and then similarly, in 1 minute, we know that there are 60 seconds. If you were to go through and multiply everything across on the top, figure out what that equals, multiply everything across on the bottom, figure out what that equals, take the top over the bottom, you should get 109.3 feet per second. All right, and that is that. Okay, this last section here is just a review of some different things from our notes with the history of chemistry. I'll make a point to say that this is not everything that you need to know about that set of notes on history. I think this just gives a pretty good summary of some of the big ideas that are going on. You are responsible for everything in that set of notes, so make sure that you're familiar with the paleochemistry notes. Most notably, try and make sure you know the vocab words, try and make sure that you know the general idea of what's going on. You know, if somebody asked you a question based on that, you know, some of the bigger ideas. Pay attention to the things where there are blanks that I had you fill in, because if I made you fill in a blank, it was probably something that was important. Okay, but other than that, you can just kind of read through here the different things I've said about what's going on in society at those given times. And, you know, if you'd like to see anything further on that, you can watch my video, the whole video on the PowerPoint for paleochemistry to review for that. Other than that, you know, this is kind of just a general guide, but, you know, make sure you look through all of those paleochemistry notes. And that is the end of this. So there will be the practice exam, of course, that you can look at as well to try and prepare for this. Other than that, just, you know, make sure this is our first test, that you're going into it prepared, and that, you know, you take advantage of all of the tools that I've given you, and that you come and see me if you need help, because that's really important.